Hi guys, welcome back to Data Every Day. Today we're looking at a fake and real news dataset, which is basically just, I don't know if you can see it, it's not having a trouble loading, but it's a bunch of news headlines and the content of news articles, and they're separated into fake and true. And as you can guess, we're going to classify whether a news article is fake or true, but using only the name of the article, the title of the article. So I have the task for today. Given titles of various news articles, let's try to predict whether a given piece of news is fake or not. And we'll use a TensorFlow Gated Recurrent Unit recurrent neural network to make our predictions. So I did a GRU video recently, but I'm going to do another one today. I have some imports we're going to use, NumPy pandas, as always, Plotly for visualization, and then all these for pre-processing. Then this is just to split the data, and this is for training the model. So let's load that in. And then I'm going to load in, we have two data frames today, two CSV files that will turn into data frames. So I'm going to have true news as the first one, and fake news as the second one. And now both of them are going to be, I'm going to load them in using, oh wait, I forgot to put a space here. Okay, I'm using pandas.readCSV, and I'm going to grab the fake article, put it in here, and the true, CSV, and put it in here. Load those in, and now we'll take a look. So check out the true ones, and check out the fake ones. So as you can see, they each have a title column, a text column, subject, and date. And what I'm going to try to do is I'm going to try to classify whether they're fake or true based only on the title. So I'm going to throw away all the rest. Just as a challenge, I want to see how good the title is at predicting the rest of the, whether or not it's fake. Alright, so what we can do is concatenate them together. So before I do that, I'm going to put on a little label column so that we know which is which. Once they're together, we're going to need that to identify fake and true. So for the true, I'll call it the true data frame, true DF, is going to be pandas.concat. So we're going to concatenate the title column of true news. So we're just taking this, and we're going to concatenate that with a new pandas series that is going to be full of zeros, because here 1 would mean fake, because we're looking for that as the positive example. And we're going to include the index is going to be the index of true news, truenews.index. And we're also going to have a name, which will be label. So if by specifying this, we will fill it with zeros. And then we're going to copy that and do the same thing, except this will be fake DF. And here we're concatenating fake news subtitle, so this one, this one, with a new series but full of ones. And the index is going to be fake news.index. Alright, so if I run that, and I take a look at these, true DF is just a series, right? Oh wait, oh no, I made a mistake. This should be a data frame. The problem is I did not specify the axis of concatenation. I want to make sure we're concatenating these side by side rather than on top of each other. So now if we look at it, now we have a proper data frame. It's just the title column from the original data frame, but with this new label added. And similarly, fake DF should be the same thing, but with ones. Alright, so now we can put them on top of each other. So I'm going to make this like total data frame called newsDF. It's going to concatenate them on top of each other. So we're true DF, fake DF. And here axis is 0. However, there will be, as it currently is, they're not going to be scrambled at all. It'll just be zeros on top of ones. So we can fix that by sampling sample with frac equals 1.0. That means the fraction of the data that we're sampling is 100%. And random state will be, let's see, 34 works. This will essentially just shuffle the data. And then because it's shuffled, the indices are also going to get shuffled. So we're going to reset the index after that's done. And I include drop equals true to prevent the old indices from becoming a new column. So if I run that, then we take a look. You can see we now have 44,000 rows, almost 45,000. And we have shuffled data. So some is fake, some is true. And you can see from these, we have roughly the same amount in each category. A little more in fake, but that's good. Okay, so what we're going to do now, I guess we'll call this pre-processing. We're going to basically take a title and strip it down to a simpler version. So there's a few filters we're going to run it through. At the top here you can see I have imported the Porter stemmer from the Natural Language Toolkit. And this is basically a nice little thing that will take a word and reduce it down to its root, you could say, its stem. So if, let's say PS will be our Porter stemmer. And let's say I want to stem a word. I'll give you an example. We'll stem, let's see, what's a good word? You can say cooking. It will just get reduced to cook, and it will also get lowercased. Okay. So any endings like ing or cooked would also go to cook. This will allow us to reduce the number of unique words in our vocabulary, and also it will allow for different articles to have like, it will allow the model to understand that cooking and cooked are actually the same meaning. So there are a few different stemmers we could use. Porter stemmer is the most common. So alright, I also imported regular expressions, which will allow us to modify titles as we wish. So let's go ahead and create this function, process title. And it takes in a title, and it's going to apply various transformations to the title. So let's call new title. It's just we're gonna start off by doing title.lower. So the first thing we'll do is just set it to lowercase. And then from here on, we're going to just keep processing new title. So new title will be, now I'm going to use regular expressions. The dot sub will allow us to substitute a pattern, like some part of the title that's captured by the regular expression. We're going to substitute it with another value. So here will be our regular expression. And what I'm going to do first is I'm going to try to find any dollar amounts and just convert that to dollar. So anytime, this is a regular expression, anytime we see a $sign followed by anything other than white space any number of times. So what that's saying is that essentially we'll see a $sign and then followed by anything other than white space. Eventually hits white space, it stops. So that will target just this. And we're going to replace that with $. And we're going to apply this substitution to new title. And this is the format for substituting. We're just going to keep doing this for different areas. Whoops. Alright, so next, what do we want to do? What do we want to substitute here? What I'm going to do is try to remove any punctuation at this point. So anytime we see quotes, anytime we see a colon, anytime we see parentheses, we're just going to remove it completely. So this is going to stay. We're going to replace it with nothing. But how to target it, all we have to do is say anything that isn't, that's what this means. You just you can place any characters in here after the caret to mean anything that isn't. So anything that isn't A through Z, or 0 through 9, or white space. That will remove any special characters. So all the apostrophes will go away, all the colons will go away, all the periods will go away, and we'll be left with just straight up alphanumeric characters. And then we're then going to take the numbers. So let's do another one. We're going to find anything that's a number, and I put the plus here to mean do it in a row. So like, if I didn't include the plus, just the 7 would be targeted. Well, actually, we'll use this one. Just the 1 would be targeted. By putting the plus, it will continue to find strings that are strung together. So now take any numbers and let's replace it with number, so that the model knows anytime we see something like this, it means sort of the same thing. It's a number, right? This too. And then I'm going to split it. So now we're going to move into a list. We're going to take new title and split it on spaces. So what that will do is basically turn the string into a list. I assume you know what split does. And now we will apply some mappings to each element in the list, just to further clean it up. Here's where we'll actually stem the words. So I'm going to apply a map, and we're going to turn it to a list afterwards. It's going to map this lambda function that will take in some x, which will be, because now we've split, it'll take in a single word that's already been processed somewhat, and it's going to return the stemmed version of that word. And here PS is our Porter stemmer. I could include the Porter stemmer in the function definition, but then we'd have to create a new Porter stemmer object every time we apply this function. So I figure let's just leave it out. And then, so we're going to apply this lambda function to new title. Actually, I have one too many parentheses inside. Okay. Alright, then we're going to apply one more lambda function, but instead of stemming it this time, we're going to strip it. So this will remove any leading or trailing white space. Alright, and then the last thing, we have the possibility after this of having the empty string in our list. So we're just going to say if the empty string is in new title, then new title dot remove the empty string. Alright, and that should be enough. Then we'll return new title. Okay, there's our function. And I'm going to create this new list. Actually, it will be a NumPy array called titles, that will take the newsdf, which is this thing, actually just the column, just the title column from newsdf, and we're going to apply that lambda function to it. Actually, not a lambda function. We're going to apply process title to it. So this will apply it element-wise to each title in the column, and that will store it in titles. This will actually be a series, not a NumPy array, which is fine. And then labels. I'm just going to make a NumPy array of newsdf sublabel. So I'm just taking this column and turning it into a NumPy array. Alright, now to take a look, see how our titles have been processed. Might just take a moment here to apply this function to each element, but it shouldn't take too long. And you can see we now have a stemmed and processed version of each title. So Sunday Screened the War on Democracy number looks like Sunday Screening the War on Democracy 2007. It has been processed into this nice little list for us. And now we can use these as our inputs. So there's a few more things we've got to do to it. Currently we can't feed it in. We're going to need to encode it first. And what we can do is use the Keras embedding layer to do our dense encoding for us. So, not markdown code. I'm going to just first, before we go on, I need to get two values. One is going to be the number of unique words in our vocabulary, and the other is going to be the maximum length of a sequence in our titles. So what we'll do is get size of vocabulary and get max length of a sequence. So we'll start with the vocabulary. This will just be a for loop. Well, actually, first I'll make a set called vocabulary, and I'm going to add to the set every time we find a new word that's not in the set. So for title in titles, for each one of these, for each line, right? For word in title, if word not in vocabulary, vocabulary.add word. Very simple, just saying if we haven't seen the word before, put it in this vocabulary. And then we're going to make this variable vocab length is going to be the length of vocabulary. Alright, and then we will get the maximum sequence length. So max seq length will start at 0, and then for title in titles, so for each one of these titles, if the length of the title is greater than the maximum sequence length, then the maximum sequence length is going to be equal to the length of the title. Very simple. Alright, we're good to go. Now we'll just print the results. So print vocab length, and print max sequence length. Alright, let's see. Alright, so we have 17,807 words in our vocabulary, and the longest title is 44 words long. So now what we can do is tokenize these titles. So we're going to create a tokenizer, and this is taken from Keras as well. I believe keras.preprocessing.text, and we specify a number of words, and this will just be the vocab length. So what it's going to do is it's going to go through and assign a unique integer to each word, and it's going to do it in order of frequency. So the most frequent word will have 1, the second most frequent word will have 2, the third most frequent word will have 3, and so on, until the least frequent word will be 17,807. So all we have to do is fit the tokenizer. So fit on texts, and we're going to fit it on titles, which is just this, and it knows how long the vocab length is. Then we're going to create this sequences, and sequences is going to use the tokenizer texts to sequences function that will use the fitted tokenizer to convert these to what it needs to be, just as I described. So we just take a look at sequences. Did I misspell it? Oh, sequences. There we go. Alright, sequences is basically the encoded version. So I can also get a word index. That comes from tokenizer.wordIndex. And if I want to see what that is, it's basically mapping a unique word to a unique integer, and it's going to do it for all 17,000 words. So these ones at the top are the most common words. And now what we can do, since we have it in integer form, so here's the sequence, right? So if you look at this, Sunday Screen, The War on Democracy, 873, 1523 to 81257. 7. We could look these up, these numbers, and they would match up to the words in the original title. Alright, so I'll remove these, and we're going to continue this a little. We're just going to do one more thing, which is we're going to pad the sequences. So right now the sequences are all of variable length, which is not so good for our model. So we're going to use this pad sequences function from keras.preprocessing.sequence that takes in some sequences and a maximum length, and it's going to basically fill in the shorter sequences with zeros, and if we have any longer sequences than max length, it'll truncate it right there. So we know the maximum length. We got it. It's 44. So that was called max sequence length. And now if we run that, look at our model inputs. These are the original sequences, but now they're padded with zeros when they're too short. So each one is 44 long, and only the ones that are actually of length 44 will have no zeros. Everything else will have zeros to fill in. And we can look at the shape of that. We see that we have all the examples and now 44 inputs. This is ready to feed into our model. So what we'll do is split it into train and test sets. Xtrain, xtest, ytrain, ytest is going to be train test split model inputs and labels. Remember, labels was just this column that we turned into a NumPy array somewhere. We can't see it right now. Right here. I took the label column and turned it into a NumPy array, and now I'm going to split the model inputs and labels into train and test sets. Alright, we can start training. We'll build our model and train. So before we start, I'm going to specify an embedding dimension. And this is going to be the dimension of the vector that we'd like to encode our words as. So basically, we're going to send each unique word. So they're encoded as, I'll probably just show you what this looks like. Each one of these unique numbers is going to be sent to a new location in a vector space, and we're specifying the dimension of the vector space here. The higher this is, the more meaning can be captured between words, and sometimes that's a good thing, sometimes it's not. There is some concept of overfitting in this as well. Like if we have too complex of a vector space, the meanings won't properly be captured, and if we have too simple of a vector space, we will not be able to capture the meanings very well. But if we get it just right, and I think 64 is pretty good for our purposes. I was trying it out earlier, but it could be improved. I'm not denying that. Anyway, we're going to send each one of these to a vector in 64-dimensional space. And I'm going to create an input layer that will take in a shape of length 44. I guess I could actually make this max sequence length, because we know that all the vectors are the same length. And then I'm going to create an embedding layer. So embedding will be tf.keras.layers.embedding, and this is the layer that actually will encode our words properly. So embedding layer takes in a few arguments: input dimension, output dimension, and input length. And so input dimension is just the size of our inputs. No, sorry, it's not. It's the size of our vocabulary. So it's going to take you could think of it like one-hot encoding. It starts off as one-hot encoded. So each one of these, if you were to one-hot encode each one of these integers in a one-hot encoded format, the dimension of a given one-hot vector would be the length of the vocabulary. So 17,807 dimensional vector, which, as you probably realize, would be just ridiculous to use those one-hot vectors as features, because that's just, you know, so many columns, so many features that can better be represented by a 64-dimensional vector. So what we're doing is taking in this one-hot vector for a word, which will be the dimension will be vocab length, and we're going to embed it in 64-dimensional vector space. So embedding dimension will be our output dimension at 64, And then our input length is just going to be max sequence length. And then we'll pass in inputs into the embedding layer. Alright, and now comes the fun part. I mean, it's just one line of code, but basically we're going to be using a gated recurrent unit, recurrent neural network. Well, basically, if you don't know what it is, let me look it up. GRU. It looks like this. I don't know if you can see it here. Here. So basically, let me open this. Okay, so if you don't know about Rnns, they're very cool. Basically, the way it works is it takes in an input, that's this thing, but it also takes in the previous word as input. So where this comes out, it loops back around and comes in this way. So it'll combine the new input and the old input in some way, and then spit out an output, and also feed it in through the next iteration. And so an LSTM is a much more complicated version of an RNN, but performs very well in sequence, time-dependent sequence tasks. And a GRU is simply, it's just a more simplified version of the LSTM that's more computationally efficient and it performs better on smaller tasks in most cases. So we'll be using the GRU here, called GRU. Will be tf.keras.layers.gru, and we're going to specify the number of units as the max sequence length. Is that correct? No, it should be embedding dimension, as we're sending in 64 a vector of length 64 after it's been through here. And then we're going to pass in the output from embedding into here. Alright, and that's it. Now we have an output layer, which will be a dense layer with one activation and a sigmoid activation function, since this is a binary classification task. And we'll pass in the output from GRU. Then we'll have a model, which will take in our inputs and our outputs, and we'll compile the model. So we have an optimizer, it's going to be atom, loss function will be binary cross entropy, and metrics, we use two metrics, accuracy and AUC, the area under the ROC curve. tf.keras.metrics.auc, name AUC. Alright, and once we've compiled it, we're going to specify a batch size and a number of epochs to train for. So batch size will do 32, and this actually doesn't need many epochs to train. I think 3 will be good. Usually the best results are found in the first 1 or 2 epochs, at least for small tasks like this. And then we're going to store our model's training history in history and fit it on the train set. Xtrain, Ytrain. We're going to give it a validation split as well. About 20% sounds good. And we'll pass in the batch size and epochs. We'll also include some callback functions. One will be tf.keras.callbacks.reduce learning rate, reduce LR on plateau. So when the model sees that the loss is not decreasing so much, it will reduce the learning rate so as to converge nicely into whichever minimum it has found. Alright, and then we will give it another callback that would be model checkpoint, and this will save the model in an HDF5 format. And basically what that'll do is we'll save the weights so that we can load in. We're actually going to specify save best only equals true. And this will save the best version of the model from a given epoch in our output directory, which we can then load up later to use for inference. Alright, so I'll train that, and while that is going, I'm going to start plotting the results. So we're going to make a plotly figure that will draw values from history.history, and we're going to plot the loss and validation loss. I'll also do this for the AUC. Labels, let's map X to epoch and Y to loss. And then we'll give it a title, which will be loss over time. Then we'll show it. And I'm going to copy this and make another one, but this will be for the AUC. So the metrics here are AUC and val AUC, and then on the y-axis we'll have it called AUC. The title will be AUC over time. You can see this is almost done, and it's looking incredibly good from our just from looking at this. And yeah, it looks like the first epoch was actually better than the second. Right, so like I said, training for very little. What this will do is it will save the weights from the first epoch if we don't get an improvement here. And it's done. Yeah, it looks like this was the best. So what we'll do now, let's look at this. You can see, I mean, this is only 3 epochs, so it's not much to look at, but the loss just continued to go up, the validation loss. It was best at epoch 1. Yeah, these are shifted. This should really be 1, this should be 2, this should be 3. 0, 1, 2, though. I guess I could call it epoch 0. Over here, the AUC was highest at epoch 0. Okay, so what I'm going to do is load. So if I look at the output directory here, we have this model.h5. I can load in the weights, load weights, model.h5, and that'll just basically change the model's weights to be the best weights from the training. So we'll run that, and then we will evaluate the model's performance on the test set. And you can see we have extraordinary results. Accuracy of 97%, AUC of 0.99. So actually, I think people were able to get this much higher. Accuracy of 99.87% in one case. And they use some advanced techniques, but it looks like we can also get some good values with LSTMs. It is important to note, though, that I only use the title column here. And it is actually remarkable that we're able to classify fake news 96% of the time based only on the title of the article. We didn't even include the contents of the article. So yeah, this just shows the power of GRUs and LSTMs and Rnns. It's just amazing. But I guess that sums up today's video. Thank you so much for watching. I hope you enjoyed it. If you did, make sure to subscribe and hit the bell for more content, and leave any comments you have in the section below. I'll see you guys tomorrow. Have a fantastic day.